So let's take a look at some processes. And to analyze processes, thermodynamic processes, we're going to use a PV diagram, okay? So concept 0 is that the vertical axis is pressure, and it's always pressure when we do this, and the horizontal axis is volume, okay? So if we change the volume without changing the pressure, that looks like this. And we'll talk about that. This is called an isobaric expansion. If we change the pressure without changing the volume, that looks like this. That's called an isochoric cooling, but we'll look at these individually, right? Obviously, you can change both, and in fact, organically, they will change together, okay? For example, if I've got a gas here at this pressure and volume, and I move the piston out, well, the pressure is going to drop because there's more distance for the particles to travel before they hit that piston again. This is just the ideal gas law. So as I increase the volume, the pressure is going to drop, even if the temperature remains constant, right? And what we'll learn here is that the temperature doesn't actually stay constant. In this case, it actually cools down as you expand like this. So just that's sort of the PV diagrams that we're going to be looking at here. On this thing, remember that every point on here, if we know the number of moles, if they tell you that it's so many moles, we can still use the ideal gas law. And you can read the pressure and the volume right off the graph. If they tell you either the moles or the temperature, you can calculate the other one because, of course, R is a constant. So we're going to use that. We can also use the combined gas law for this. Assuming it doesn't leak, and I've never seen one where like the N changes, okay? Anyway, let's look at our isobaric process here. So here's an isobaric expansion. And what's happening here is, and this could happen, this is a very realistic process, right? Let's imagine we've got an ideal gas, and the pressure in here is either atmospheric pressure, or if this piston has mass, then it's the atmospheric pressure plus the pressure exerted by the weight of this piston, okay? Now, if we allow that piston to move freely, if I put this over a flame, that's supposed to be a flame even though it's blue, right? The temperature of this gas will go up, the particles will hit with greater force, and so it will move this piston out, and that's what's going on here, okay? So this is cool, this is hot, right? That is, we had to add thermal energy in this to make that piston move up, okay? So really a couple things happened here, right? We had a change in temperature. We also had work happen, right? Okay. And then if we look at the other process, this is just the opposite, right? It goes from hot to cool. And instead of putting a flame under here, right, we put ice cubes. That's what they look like, right? Okay, and then if we do that, the temperature is going to go down. The piston will settle because the gas is moving slower and slower, okay? So, and then, just a little bit of vocabulary here. Iso means same, right? Baric is pressure, like a barometer measures pressure, okay? Let's look a little bit at the formulas that we'd use for this. We've got work is pressure change in volume, right? This would be a positive work because the change in volume would be positive. That is, we go from some number here, right, to some number here. It's a bigger number. It's a positive change in volume. And then the compression would be negative work because it's work done on the gas, okay? So we're going to use work and this is one where we can just calculate that, right? We can also, if we know the number of moles, we can figure out that temperature. We can use PV is nRT. So if they tell us the moles, and we can read the pressure and volume off the chart, we can figure out the temperature, right? And so you can figure out the change in internal energy here using the change in temperature. Or, and this is a shortcut, it's not in the packet, is that the change in U also equals 3/2 P delta V. And the reason for this is that, well, PV equals nRT, right? So here we've got NR delta T. That's the same as P delta V, right? So we can just plug it in. That's kind of cool. And they throw that out. You'll see it in the mark scheme, like, oh, they use this. So, there it is. All right. So those are kind of the formulas. That's an isobaric expansion. Just remember, isobaric is same pressure. So if it moves along and the pressure doesn't change, that's isobaric. Okay?